All right, now that I'm composed. So a sapling problem with, we have an axial X group, an equatorial Y group, and then the other bonds are drawn and you have to label if they're axial or equatorial. So let me, if you'll permit me to arbitrarily number this so I can ask you some questions so I'm not just up here talking. So I've just numbered the ring, 1, 2, 3, 4, 5, 6. You can come grab a seat. So X is axial, Y is equatorial. If we look at carbon 2, so that's right next to the top, that carbon is pointed down. So the axial group on that carbon should be pointing what direction? It's pointing down. So it's that bond that I just drew. So that's axial. So the equatorial group is going to be, since we're on sort of the left side of the molecule, it has to point this way. So the other thing this question is asking you, what groups are gauche to Y? You're only going to have a gauche, well, I take that back. So a gauche relationship is a 60-degree dihedral angle. So the equatorial group that I just drew is gauche to Y. Does everyone see that? So let me call that, I'm going to call that A, and I'll call this one B for using letters. So Y is gauche to A. It turns out that X is going to be gauche as well, but this question is specifically asking you for Y. So if we look at carbon 3, the axial group is going to be what? Up or down? It's going to be up. So one thing I want to point out, I'm going to call that C. Notice the relationship between carbon 1 and 3, how those axial groups are parallel to one another. So if you're skipping every 3, then carbon 5 is also going to have an axial group up. So I'll draw that in. So let me put in the equatorial group for 3. It's going to point that way. We'll call that D. Now carbon 4, the axial group is going to be what? It's going to go down. So the theme here is that it's alternating, right? So down, we'll call that E. The equatorial group is going to point this way, and that's going to be F. So let me ask you a question. What's the relationship between C and F? What's that? Not so much. If the question said, are C and F cis or trans, what would the answer be? They're going to be cis because they're on the top face of the molecule. So C and E are therefore trans, right? What would be the dihedral angle between C and E? It'd be 180. So if you don't get that, you can look at a model and then look at a Newman projection. So let me just go ahead and put, so E, F, G, H, I, J. So we've finished it off. So the groups that would be gauche to Y. Actually, you know, both of those substituents on 2 and 6 are going to be gauche to Y. Because they're both, the dihedral angle between A and Y and B and Y are both 60. So maybe let me just draw that in a Newman projection so we all can see that.
Has it loaded about what the answer was?
No, it's
was, I can't remember, but I think there was 3 or 4 gauge.
There's going to be 4. So let's do a specific example, just so that everyone can see it, instead of using these letters here. Yeah, so everything on 2 and 6 is going to be. So let me put I just don't want to use like letters because it's sort of meaningless. So say it was this example, and I'm going to draw it just like this other chair. So that would be your 1 carbon. Then all these other things are just going to be methyl groups. And so this should be a little bit more easy to see. So you have carbon 1, 2, 3, 4, 5, 6. And so we're going to look down the 1 and 2 bond in a Newman projection. So the front carbon is carbon 1. So what should I draw at the top? What should I draw right here? We're looking down this bond. It's going to be that hydrogen, right? And then what's right here? CH3. And then here, that's going to be the carbon 6. So we have H, CH3. So this thing here is going to be carbon 6. I'm not going to complete it yet because I want to put in the back carbon now. So there are your two methyl groups. I'll actually put in the CH3. Then this other bond is going to the other part of the ring, and that's actually going to be carbon 3 in this case. So when you do this sort of Newman projection for a cyclohexane, you want to draw like 2 of them. So if you're looking down 1 and 2, the other thing you're going to look down is 5 and 4. So this is your left eye, and then it's going to get kind of sloppy here. And this is your right eye. So this has to come back up. That's carbon 5. This is carbon 4. Those things only have hydrogens. And carbon 6 had the 2 methyl groups, CH3 and then CH3. So this interaction here, that's gauche, 60 degrees. And then this interaction is gauche as well, 60 degrees. So you also have it looking down the 1 and 6 bond as well. So total there's 4 relative to that methyl group. And I'll give you these energy values so you don't have to worry about memorizing them. You just have to be able to see them when you see them, I guess. So I think we answered that one. Any other cyclohexane ones while we're on this particular slide? let me pose a question to you so you can get into my head, see my thought process here. So I like to ask like multi-layered questions. So if I give you a name, can you convert that name into, say, a chair? So let's look at, let's say, trans 1,3 dibromo cyclohexane. So how could you make this somewhat easier on your life? I would just draw a flat cyclohexane first. So there's your hexagon. Again, you can plunk down the first substituent anywhere you want. I'm going to put one, I'm going to say that's a bromine. Say 1, 2, 3, 4, 5, 6. So if I drew the bromine at position 1 going down, what should the bromine at position 3, what type of bond should I use there? So the bromine at position 1 here, I've used the dash to signify that bromine's facing the bottom face. We have a trans relationship between the 1 and the 3 bromines. What sort of bond should I draw at the 3 position for that bromine? The wedge. Any golfers out there? We'll use the wedge here. So we've sort of drawn it one way. How would we draw a chair for that? So depending on how you draw your chair, say for example I draw it this way. And say I'm going to number these carbons this way. 1, 2, 3, 5, 6. So I've arbitrarily numbered them that way to help give you some mental dexterity in how you think about this. So you play soccer, right? So you need to, you can learn like plays, but whatever is in the game you have to react to, right? So this is sort of like that. I don't want you like memorizing anything particular. You should be able to like adapt to the problem. So in this chair cyclohexane carbon 1, we from the flat cyclohexane we have that bromine going down. What sort of bond should the bromine have in carbon 1 in the chair? Equatorial or axial? It's axial, so it's going down. If I put that hydrogen in, now you can see the hydrogen's up, the bromine's down. So we're going around the ring 2 to 3, and we know it has to be a trans relationship. So if that bromine's on the bottom face of 1, it has to be on the top face of 3, and the bond should be what? Equatorial. So without me drawing it, if you do a ring flip of that, what's the relationship going to be? What is the bromine of 1 going to be and the bromine of 3 going to be when you do the ring flip? If it's axial in 1 and you flip it, what's it going to be in the other chair?
That's where you lost me this morning, so...
Does anyone have their model kit? We need to have like a race who can build the fastest cyclohexane. So a lot of this moving forward, let me just be clear. So like, I have to assign you a grade, but I don't want you to think that like I'm giving you that grade. You know what I mean? It's the work that you put into this. The next chapter we get into is stereochemistry. So you're definitely going to have to think in 3D, because I've been telling you things, but I haven't been giving you like the whole story so far. And we're gonna take it up a notch, and we're gonna look at the specific stereochemical arrangement of substituents. Then that's going to lead into the reactions. So the reactions occur with specific trajectories. So if we wanted to take this molecule and react it with something, you can predict where it's going to react and why. So let me, while she's doing that, I'm going to explain on here what you need to do. But once she has that made, we can pass it around and you can all flip it. So we're going to take carbons 1 and 4. Those are the carbons we're going to flip. We're going to take carbon 1 and flip it up. So see how it's pointing down right now? It's going to point up in the chair flip. Carbon 4 we're going to take and flip down. Because it's up, it's going to go down. So when I flip it, I'm drawing the other chair. Let me just renumber it so you can see how things track. So 1, 2, 3, 4, 5. I would encourage you as, oh look, a lightsaber. Use that. We got Darth Vader here. So the lightsaber is pointing to carbon 1. But now see the relationship like 5 and 6 here? Oh, it's kind of annoying. See how it looks like carbons 5 and 6 sort of like shifted over? It's really a matter of perspective and how things are drawn. So, but you do see carbon 1 is now up, 4 is down. So if the bromine is axial in one, it's going to be equatorial in the other. So that hydrogen goes up. That bromine's still down, but now it's equatorial. At carbon 3, this bromine is now going to be axial. So you don't ever change this relationship trans. When you do a ring flip, that has to stay the same. The patient is dying on the table. You already have 6 made. So if you don't know, the black ones are SP3. They snap into place. Once you have one made, just leave it made. Did you make a cyclopropane this morning?
No.
You didn't want to ruin your bonds? They will break. So that does sort of give you an indication that they are strained. So here we go. So I want you to hold one of them in your left hand and carbon 4 in your right. And then I want you to flip one and then flip the other. And watch how the relationship of these bromines change. So I want everyone to do that.
Wait. Okay.
Yeah, well, whoop-de shit, who cares? So the one in your left hand right now is axial, correct? That bromine. With your right hand, put your right hand on carbon 4. Now flip carbon 1 up. Just like,
Which one's
The one in your left hand. Now flip carbon 4 down. So bromine at carbon 1 is now what disposition? It's equatorial.
Equatorial.
Right. Whenever you do a chair flip with a model like that, you have to have your hands on carbon 1 and 4. One goes up, one goes down, or one goes down, one goes up. They have to be 1 and 4. If you do it 1 and 3, 1 and 2, you're not doing it right.
So like, let's say on the exam, it was like, we got like a model like that was numbered. Would you be like, flip 5 and 2, and what does it look like, or something like that?
Let me get another slide. We'll do an actual problem. So we'll do a different relationship, I guess.
And also, does the chair flip, does it always go clockwise?
I don't necessarily know what you're meaning by that. Let's do a problem and then maybe re-ask that and see if I answer it. So say I want to put OH here, and then I want to put methyl there. So the question could be, given this cis 3-methyl cyclohexanol, which of the following A, B, C, or D is the correct chair flip? So again, I'm going to number these. I'll number them according to how it's named, but we're gonna flip different carbons. So this is going to be 1, this will be 2, this will be 3, 4, 5, 6. This is what I mean by like relative numbering. 3 and 6 are the carbons we're going to flip.
So it's always that close. No, just kidding.
So it's the way you're looking at it, because we're looking at it sort of dead on. And if you were holding this, the way this is drawn, it would be 3 and 6 would be the ones you're holding and the ones you would flip. So again, carbon 6 is going to go down, carbon 3 is going to go up. So all you're doing is drawing the mirror image of this chair. Does everyone understand what I said about mirror image? So let me put these numbers in. I said 6 went down, right? So here's 6, 5, 4, 3, 2, 1. So it's important to number like that so you understand how these things flip. So in the chair flip, what is the hydroxyl group going to be? It has to be up, right? That's not going to change. So on carbon 1 in the chair flip, what sort of bond is up? You have 2 choices.
Axial.
What?
Axial.
It's going to be axial.
So when you flip it, it'll still point the same direction?
Yes. So that's maybe one thing you can do that doesn't change. So just remember that. Up is up, down is down. The question really is it axial or equatorial? That's what we're getting after. So carbon 3, the methyl group, what is that going to be?
Axial also.
It's going to be axial. So if you look at what you started with, let me just say left chair, right chair. The name of this compound is cis. That does not change in a chair flip. Both substituents are up in both chair flips, right? So that's one thing that you want to keep in mind. What you're really looking at now is which one of these is more stable. And so go ahead.
The left.
The left one is. And why is that?
Because the substituents are farther apart. I don't think that's the right reasoning.
So the way you want to think about it, in the right one, see this relationship?
Oh, they're...
I'm gonna color over it in green here, which you guys can barely see, but this is called a 1,3 Diaxial Interaction. And it's basically stating that, again, the reason you want to use these models is that these substituents take up space. And if you just look at it on paper, you're like, oh, well, I don't really see the reason, but man, that's not going on there.
You have to shove it in.
I'm gonna do it that way, make my life easier. So here's a 1,3 diaxial interaction. And you have to imagine, these things have van der Waal radii, right? So instead of being this tiny little sphere, it's like big. And that oxygen's big. So these things are banging into one another. So what does it want to do? It wants to chair flip so that they're both equatorial and they no longer have that interaction. So the more equatorial substituents you have, the more stable the conformation.
So if it's equatorial before the chair flip, it's going to be axial after the chair flip?
Yes, always.
But it would prefer to be in like the first one with the equatorial ones.
Yeah, so maybe let's write down a couple observations here. So I'll just write axial, CF, chair flip, equatorial. Equatorial, chair flip, axial. Substituents prefer to be equatorial. What? I can't spell. So your question about clockwise or counterclockwise, is that in relation to how this is like numbered?
It's yes.
So I was sort of doing it just like relatively speaking. Maybe let me give you a name, then we can convert that name to a structure.
I was just gonna ask him like in relevance of how in the last problem, like the numbers shifted the opposite way, like they went clockwise.
That was just how I did it. I didn't do it for any particular reason. You're going to end up with the same thing no matter what. So let me ask you a question. We'll see if we're all on the same page here. So say you were drawing this flat cis 1,2 dimethylcyclohexane. Say I drew it like that. Is that second drawing the same as the first? It is. So don't let my don't let me influence how you're thinking in terms of like your gut reaction. So right now, what you guys know, you can take that molecule, flip it over, and place it on the first one that was drawn, right? In chapter 5, we're going to do that, but you're going to see that they don't always match up to be the same, and that's where it gets different. So at this one, to answer your question, that could be like I arbitrarily started numbering it one way, then I drew both wedges, the other one I drew both dashes. It's just having the versatility to realize that.
I have a question.
Yeah.
Are pKa value, acidity, all of this stuff going to be already, right?
I'm going to give you that list from the textbook, so that you don't have to worry about like memorizing things.
Just be able to interpret.
You do have to know how to interpret it. So the biggest challenge there is, if you're given a polyfunctional molecule, say with 4 different functional groups, can you identify, relatively speaking, what the pKa of each of those are? Because they're not going to appear on that table exactly the same, right? So, for example, try to pull one out of this book here. So this molecule is called capsaicin, and it has the following structure. So this is a polyfunctional molecule. By this point in the semester, you should be able to determine the molecular formula. So that's counting C's, H's, N's, O's, other heteroatoms. Identify functional groups. Keep in mind what infrared spectra look like for functional groups. Unique carbons, unique hydrogens, and now for this module, acidity. So looking at that, why don't you throw out some functional group names you see, and I'll write them by the functional group. So I've underlined an H there. What other functional groups do you see? Alkene. I'm going to put this H in. So I'm going to underline specific H's, and then what I'm going to ask you to do next is to rank them. So I see a couple other functional groups we can pick out. You have a carbonyl with a nitrogen. What's that called?
Aldehyde?
Nope.
No.
What?
It
Amide.
isn't.
So here's an amide NH. What about when you have carbon, oxygen, carbon as above that alcohol? What's that called? An ester has what? 2 oxygens. What's the other one with 1 oxygen?
Ether?
Ether. So you have 4 functional groups. Each of those has a proton. Let me ask you a couple questions. We'll sort of narrow it down. What's the most acidic proton of the 4 that are underlined? The alcohol. This is a special type of alcohol. If you have that pKa chart, what's the pKa of that alcohol? What is that OH bonded to? A benzene ring. So if you look on your table, this one's more acidic than a normal alcohol. So this would be an instance where you're given that table and you got to scan it. So for example, I could give you 4 numbers of this type of alcohol. What is the pKa? So why don't you, does anyone else have the table, Andy? So we said that alcohol is bonded to a benzene ring. What would be the shorthand notation for a benzene ring? So everything on that table is sort of condensed, right, in shorthand?
Wouldn't be this one.
No, that's too acidic.
This is really long one.
This one. C6H5 CO2H. 4.2.
9.9.
So, yeah, it's the 9.9, C6H5.
So you just find like the least acidic one that has.
So the reason it wasn't that one you pointed to, it has the C6H5, but this is a different functional group. So what I'm asking you is, I'm going to circle this fragment of the molecule in green here. That's the substructure you're looking for on this table. So this is the exact molecule that's on that table, C6H5OH. And the acidity of that proton is listed as 9.9, so that's the most acidic. What does that mean if something's the most acidic?
I have a question.
Yes.
So when we say pKa, are we just talking about
About,
acidity?
yeah, so this is the number. So to put that into context, the pKa is the number of these 4 functional groups, you have 4 acidic protons we have identified. If you treat that compound with 1 equivalent of base, the pKa determines which proton is abstracted. So it's going to be that alcohol because it has the lowest pKa.
So it's the lowest pKa and the highest Ka for the most acidic.
Yeah, so that's the relationship. A large Ka gives you a small pKa.
Just to get Ka, you move the products or whatever again.
Yes, so it's an equilibrium expression. So just to review that, so say this was an acid dissolved in water. Ks are usually equilibrium expressions, and so when you're doing that, it's the concentration of the products. So again, we use these square brackets to indicate molarity, divided by the acid. Remember, the concentration of water gets folded back into the Ka is a constant. So if you look at that equation, what this is telling you, if something ionizes to give you a lot of H3O plus, that means this concentration is really big. That's a small number. So a big number divided by a small number is a really big number. And the pKa of that ends up being a smaller number based on the math that you do. So pKa is the negative log of the Ka.
Can you work on a problem where we would use that equation? Or is that not?
Can I? In theory I could, but I'm not going to. Not to be a dick or anything, but I don't like doing those type of math things in organic. I want you to think qualitatively about it.
So we won't have to.
I'm not going to ask you to calculate any specific number. I want you to really understand it qualitatively.
I have another question.
Yeah.
On that same day that we did the pKa and Ka value, you talked about the shift of the acidity
Right.
between the two sides, and I wanted to see if we don't have to like tell which arrow was correct. Like,
Yeah, so in that case, you would be given like a system that has two reagents that are acidic. Then you'd have to look at the table and see which way the equilibrium is going to lie. Let me see if I can find a specific example that we can do. So I think I'll pick one where I sort of stack the deck here. So let me make sure there's one on there.
so really with those type of questions, you would just be looking for the pKa and the arrow would go the opposite of the strawberries.
Correct.
Which would be the weakest pKa value.
Yes. So let's I don't want to like just give you a problem you're going to see on the exam. So I'm taking a little bit of time to think about this. Well, let's try this. We'll see if it works out.
Do you have any office hours tomorrow?
I'll probably have another review session tomorrow night. So let's look at this. So I'll ask you a couple questions. You're given two reactants. First, we'll draw the acid-base reaction. Then we'll determine which side the equilibrium lies. Can you tell me the name of the reagent that's drawn to the left? the nomenclature review. How many
That'd be,
carbons? What's that?
Carboxylic acid.
It's carboxylic acid. So how many carbons are in the chain? 2. What's the parent of 2 carbons? So ethane, if it's a carboxylic acid, it's ethanoic acid. So the common name is acetic acid. If you have vinegar at home, do you all have a bottle of vinegar at home? You know what vinegar smells like? So give it a nice deep inhale, see if you pass out. So that's what ethanoic acid is, acetic acid. You actually eat it if you like going to Olive Garden. That's what the salad dressing is. It's acetic acid. So that's an acid. It's in the name. So the other reagent is a base, and it's called ammonia. So we want to draw what happens in an acid-base reaction. What's the verb that a base does? What is the action of a base?
It accepts the proton.
It accepts it. So another way of saying that is that lone pair is going to abstract that acidic proton. What's the pKa of a carboxylic acid? So 4.75. I'm going to write that number here in blue. Okay, so pay attention to this arrow. You're going to start doing this in the next module. The ammonia is a base. The arrow starts at the lone pair, and it's abstracting that hydrogen. You're forming an NH bond. Hydrogen can only have one bond, right? So you have to break the OH bond. And how do you show the arrows? Well, the electrons in the OH bond go onto oxygen. And how do you rationalize that? Oxygen from the periodic table up here is close to fluorine. It's electronegative. It can accept them. So what are the products of this? So I left some things off. What did I leave off, and how should I fix it? Charge on what? Should be what? And so the nitrogen has to be balanced. So this is an acid-base reaction. You have an amine base abstracting a proton from an acid. We want to predict the equilibrium now. We have one pKa, we need another pKa. Can you look on that table and tell me what other number I should write?
For the initial reaction? Like the initial substituent, like the ammonia?
You could do that, but that's not necessarily the value that we would want. Because you have a pKa on the reactant side. Now you need a pKa on the product side. So what value would it be then? So 9.2, that's the pKa that we're looking for. Because you want a pKa on both sides of the equation here. So we said this was 9.2. So tell me how I should draw the arrow in between these two. Which is going to be favored, the right side or the left side? The right side, because it's pointing towards the weaker acid-base pair. So I would draw that with a longer arrow this way and a shorter arrow back that way. So does everyone understand what we mean by sort of like the length of these arrows here? Yep.
How do you know which one to get the pKa value for to be axial?
So the question is, how do you know which functional group to get the pKa value for? Why don't you look on that table and look up the pKa value for ammonia itself? So like you said 38, right? Yeah, so that's not really acidic, right? So the what you're going to learn over this course and the next course is what groups are really good acids and what groups are really good bases. So obviously carboxylic acid is an acid because it's in the name. Amines are good bases. That lone pair wants to abstract a proton. So in this reaction, the pKa of the ammonia itself really doesn't play a role. Because what that's telling you, ammonia is a weak acid. So if you were to abstract a proton from ammonia, what would you get? You'd get NH2 minus. And so if you look, remember on this table, when you have really weak acids, their conjugate bases are really strong. So we use that conjugate base of ammonia as a really strong base to do other chemistry. And again, I don't want to like overwhelm you with stuff because you're going to learn that in like chapter 6. But so for now, I would say I'll try to be pretty clear in the questions about like what specifically I want you to consider, so it's not ambiguous.
Wait, so stereochemistry isn't on this exam?
So stereochemistry is not on this exam. You're going to be taking a quiz in Sapling on stereochemistry. So again, I don't like to overwhelm you with the number of chapters per exam, because then, I don't know, it's like eating at a buffet. You know, you eat too much and it's not satisfying. So if I do 4 chapters per exam, you're not going to retain anything, basically.
Okay, the area, where did you say the area points to in the equation?
For which one?
This one that we just did. I know you said it pointed to NH4.
Yes.
Plus, the area points to the strongest acid.
No.
But it's pointing to the strongest acid right now. Right?
Are you talking about weaker?
Oh, right, never mind.
Yeah.
So let me just write that down. The equilibrium arrow points toward the weaker acid-base pair. So one skill you want to be able to demonstrate, given an acid, what's its conjugate base, blah, blah, blah. Maybe let me pick one out of here just to refresh your memories. So I didn't specifically cover this in class, but we'll see how you think about it. So consider you have cyclopentene. and you're reacting it with this compound boron trifluoride. And I'm going to tell you BF3 is a Lewis acid. So I'm telling you what the acid is. So the cyclopentene is what? It's the Lewis base.
This is on the room picture. When I drew this out, like how we do the regular proton or carbon chain, I got this answer originally when I counted like 1, 2, 3 this way. But this is the answer when you count backwards. And so I guess it does matter if you count backwards.
The carbon chain. So let me draw it up here and sort of explain. I'm gonna sort of cheat here because I don't want to draw out CH2s and CH3s. So I have to sort of draw it slightly different. So you were asking about, you were counting it. This is a sapling problem, but I've drawn it sort of different. I've like flipped it.
Well, when I drew it, like similar to that, I was counting from left to right, and it was like in the 2 position and like 4 position. But when you read it backwards, it's like in the 5 position, 8 position, or something like that.
Yeah, so when you're given a problem like this, you have to identify the longest chain. And so it's sort of like, I don't know if like you went on road trips as a kid and you had like an actual atlas that you had to read. Now Google Maps just tells you the route. But you can take different routes along this carbon backbone, right? And so you really have to examine all the routes before you make a final decision. So let's see if we can count the longest chain. And I'm going to arbitrarily start at one place. Say I start here, and I'm going to do it in red. 1, 2, 3, 4. I know that I could go here as 5, but I know that's not going to be the longest chain. So I'm just going to erase that. Call this 5, 6, 7, 8, 9. So it seems like the longest chain is going to be 9. So we sort of determined that based on the route. Now what you have to do is, we've numbered it one way, but clearly this isn't the right way. Because go ahead.
If you do it that way, it's 2 position, 5 position, dimethyl.
So yeah, let's name it this way, just so we see. And I'll name it in red, and then we'll do it again in blue. So we have, what are the substituents here? I'm going to circle the longest chain. So we sort of learned how to do that. The longest chain is 9, so that equals nonane. Then the things hanging outside the chain, we have a methyl, a hydroxy, and a propyl, right? 3 carbons. So the parent is 9 carbons. The main functional group is an alcohol. So we can sort of build this name, I guess, backwards in a way. So it would be 6. So instead of nonane, we're going to drop this E and add OL. The 6th position tells you where that hydroxy group is. We have methyl and propyl. So if we're sort of doing it backwards, P would be the next part of this. So 4-propyl. And then what's going to go in front of that is going to be 2,5-dimethyl. So I'm running out of room here. Try to squeeze it in. 2,5-dimethyl, 4-propyl, 6-nonanol. So I'm going to take that longest chain and I'm going to number it the other way in blue. And I skipped a carbon. 5. So there it is the other way. We already know what the substituents are: methyl, propyl, and alcohol. The alcohol is the main functional group. Now it's at the 4 position. And so the reason that this is going to be the correct name is because the main functional group has the lower number. Let's write it out and I'll explain a little bit more about it. So the methyl groups now are at 5 and 8. The propyl group is at 6. So we have 5,8-dimethyl, 6-propyl, 4-nonanol. And so your question was probably, if we add these, you have 6 plus 4, that's 10, plus 5 is 15. So that gives a total of 17, right? What about with blue? We have like a boatload, right? 4 plus 6, that's 10, plus 8 is 18. Plus 5 is... So is your question that number is greater than the other one? Is that what you're getting at?
No. It asked, like, it gave the structure and it said, what is the name of it? So I was assuming the name was what was in red. But really the name was what was in blue. So I was asking, how do you know which way you're supposed to count it? Left from right or right from left?
So how do you count it is...
Because they were both an answer choice.
The right one is going to be the one where the parent functional group has the lowest number.
Oh, I thought it was like your overall number that you were worried about. So your parent group takes priority.
Yeah, so that's sort of like the twist on this, right? You have both of those things to consider, but what's going to win is the parent functional group has the lowest number.
So you would need to count both ways
Yes,
first and then see which one is the lowest.
correct.
Would you have to do that on multiple problems or is this one just like this?
It's a good strategy to do both. And if I could give you a piece of advice, like especially if you're a pre-professional student, and I know I've said this a lot of times and I really want you to take it to heart. When we start learning reactions, the reactions can go in different pathways. So it's not just going to be one path. You're going to get to a point where it could go path A or path B. You have to absolutely consider both paths because you're going to evaluate the products of each of those or intermediates of each of those paths. If you just go this way and you don't consider the other way, then you're really hampering your ability to get the right answer. You have to consider both. So, like on paper, I would do it both ways, evaluate and then choose.
What confuses me with that is thinking if we had like 4 of them and there was 1 in the 2 position and the 3 position or something like that, say 2 and 3.
Right.
Yeah, it starts getting confusing.
Yeah, I'll try not to be as sneaky or tricky. I mean, it can be like if I could design questions that are really like subtle, but overall it's the main thing, or you learning how to name things. This one, yeah, I guess I could see the issue there, where you might think it's the red one, but I guess the rule of thumb is that the main functional group has to have the lowest number. So again, there is a sheet, like that sheet you have, that handout, that tells you the priority groups on one of those that you'll want to review. So I guess if you have questions, you can email me, but otherwise I'll send out like a SOAR email or a text reminder. Probably meet in here or that other room tomorrow as well.